imagine two AI programs,
Yeah.
right? Just locked in this pitch black room.
Okay.
And one of them is an artist, just wildly throwing random paint at a canvas. And the other is a critic who's basically looking at the canvas and yelling, "That is not art."
Right, but neither of them actually knows what art is.
Exactly.
Yeah.
Neither of these programs has ever been told what a human face looks like. They don't know what eyes are or hair or lighting.
Yeah, they're completely blind to the real world.
But somehow, through just pure, brutal, relentless competition, millions of rounds later, they eventually paint this photorealistic masterpiece.
It's pretty wild when you frame it like that.
It really is. So if you've got a dark mode IDE open right now, maybe you've got a compiler churning away in the background, and you're looking to upgrade your mental models around artificial intelligence, welcome to tonight's deep dive.
Glad to be here.
Because tonight, we are pinpointing a very specific, really pivotal moment in computing history.
Yeah, we are basically looking at the exact moment when machine learning evolved from just categorizing the world to actually generating it.
Which is a huge leap.
Oh, massive. Because for decades, the entire paradigm of computing was built on explicit instruction.
Right. You write the logic, you define the parameters, the machine executes.
Exactly. And even early machine learning was essentially just drawing these incredibly complex mathematical boundaries to, separate cats from dogs.
But tonight we are breaking down generative adversarial networks, GANs.
The famous GANs.
Yeah, and what is so profound about GANs is that they aren't just this clever architectural pattern. They represent a fundamental philosophical shift.
Right, because explicit instruction was replaced entirely by a zero-sum game.
The system isn't told how to do something. It's just thrown into a simulation where it has to figure it out purely to survive.
And to really understand how radical that was, we have to look at the landscape back in June 2014.
Okay, set the scene for us.
So Ian Goodfellow, who was a PhD student at the time, is at a bar in Montreal.
As all great tech origin stories start.
Naturally, yeah. And he gets into this heated argument with his friends about the state of generative models, because back then, the industry standard was something called a variational autoencoder.
Hold on, before we go further, let's just clarify that for the listener.
Yeah.
What exactly made a variational autoencoder the standard? And why were Goodfellow and his friends arguing about it at a bar?
Well, variational autoencoders, or VAEs, they were mathematically very elegant. But visually they were terrible.
Blurry. Right?
Yeah, exactly. The way they worked was by taking an image, compressing it down into this tiny statistical representation, and then trying to reconstruct the original image from that compressed data.
Okay.
The problem is their loss function, the way they measured success, was based on minimizing the average difference between the pixels.
Right. And when you average things out mathematically...
You lose all the sharp edges, you get these highly blurred, fuzzy, just really unconvincing images.
So Goodfellow is sitting in this bar, frustrated with blurry images. And instead of trying to tweak the math of a single neural network to make it draw better, he just flips the entire paradigm.
Completely flips it. He thinks, what if you build two separate neural networks and pit them against each other in a street fight?
Which is such a chaotic idea. And he actually goes home that very night, codes the architecture, and it works on the first try.
Which is absurd.
Right. If you write software for a living, you know that is basically a statistical impossibility. First try. Come on.
Yeah, Jan LeCun, one of the founding fathers of deep learning, he would later call this the most interesting idea in the last 10 years of machine learning.
Is that big of a deal?
It is, because Goodfellow coded two distinct combatants.
Oh.
First, you have the generator.
Okay, the artist.
Right. Its job is creation.
Yeah.
It takes a vector of random noise, basically just 100 random numbers drawn from a normal distribution, and it runs it through matrix multiplication to output an image.
And on epoch 0, like the very first pass, that image is just TV static.
Right. Oh, pure garbage pixels, just noise.
Okay, so then you introduce the second combatant, the discriminator.
Exactly. The discriminator acts as the judge. You feed it an image, and it outputs a single number between 0 and 1.
And that number represents what?
The probability that the image is a real photograph from your training data set rather than a fake created by the generator.
Got it. So initially, the discriminator looks at that TV static, compares it to a real photo of a face or whatever, and just easily flags the static as fake.
Right. It's a trivial task at first.
But here is the critical part. You take that failure and you mathematically update the generator's weights so its next attempt is slightly less staticky.
Yes. And then you also update the discriminator's weights so it catches the new, slightly better fakes.
It's a classic minimax game, right out of game theory.
Exactly. The discriminator is trying to minimize its error rate, while the generator is trying to maximize the discriminator's error rate,
They're locked in a mathematical arms race.
searching for a Nash equilibrium.
And at that theoretical equilibrium, what happens?
The generator is outputting flawless photorealistic images, and the discriminator is outputting exactly 0.5.
Because it's essentially flipping a coin at that point.
Right. Reality and the algorithm have become entirely indistinguishable to it.
You know, you see a lot of tutorials use this analogy of a counterfeiter and a detective to explain this dynamic.
Yeah, that's the classic one.
The counterfeiter prints fake money. The detective learns to spot the watermarks, so the counterfeiter buys better ink.
Sure.
But honestly, looking at the actual mechanics of the code, I don't think that analogy holds up at all.
Really? Why do you say that?
Well, because a counterfeiter knows what a $100 bill looks like.
Right.
They have a reference point they are trying to copy.
Oh, that's a good point.
In a Jan, the generator never once gets to look at the real training data. It is completely blind.
It literally only sees the gradient from the discriminator.
Exactly. That's why the artist and the critic in a pitch-black room is a much more accurate mental model. The artist throws paint, hands it through a slot in the wall, and the critic just says, nope.
And then the artist tries a jagged line. Closer, but no.
Right. The artist adjusts purely based on the binary feedback of the critic. It is wild to me that neither network possesses a programmatic definition of good art.
They don't. That definition organically emerges out of the friction between them.
It's beautiful in theory.
The elegance is undeniable, but the reality of implementing it, that is where we hit the engineering nightmare.
Oh yeah, let's talk about the nightmare.
Because for years after Goodfellow's Montreal bar epiphany, making a Jan actually converge was considered dark magic in the machine learning community.
I can imagine. Two dynamic systems continuously shifting underneath each other. That is incredibly unstable.
Highly unstable.
Like if I'm a systems engineer and I hear two separate models optimizing against a moving target, my brain immediately screams race condition.
That is basically what it is.
Let's get into the specific failure modes because they are brutal to deal with. Starting with the most famous one, mode collapse.
Mode collapse is fascinating. It happens because the generator isn't actually trying to map the entire diversity of the real world. Its only objective, its only purpose, is to fool the discriminator.
Right. It's lazy in a way.
Extremely lazy. Imagine the generator is trying to create faces, and by pure chance, it outputs a slightly blurry picture of a man with glasses that happens to perfectly exploit a mathematical blind spot in the discriminator's current weights.
Okay.
And the discriminator scores it a 0.99.
Oh, the generator's going to ruthlessly abuse that exploit.
Absolutely. It's going to stop trying to draw anything else and just pump out that exact same man with glasses over and over again.
Like a one-trick pony musician. They realize the crowd cheers whenever they play this one specific four-chord progression, so they just refuse to play any other song.
Exactly. And the worst part is, if the discriminator's weights update and it finally patches that blind spot, the generator doesn't suddenly learn to play a full symphony.
It just wildly oscillates to a second trick.
Right. It jumps to a different exploit. It never actually learns the underlying distribution of the training data.
Which brings us to an even more fundamental pathology, which is vanishing gradients.
Ah, the seesaw problem.
Yeah, the dynamic between the networks is often described as a seesaw. Because if the discriminator gets too smart too quickly, it just completely dominates the game.
It rejects every generated image with absolute 99.9% certainty.
And mathematically, when the discriminator is that confident, the gradient, that mathematical slope that tells the generator which way to adjust its weights, it just flattens out to zero.
Right, the signal completely dies.
To put that in software engineering terms for you guys listening, imagine you're running a massive unit test suite. But instead of the terminal giving you a stack trace or telling you which specific line of code failed.
The terminal just prints code is bad every single time you compile.
Exactly. You have absolutely zero debugging signal. Without a gradient, the generator has no mathematical direction on how to improve. It just freezes.
And this created a massive, massive operational problem for developers. I mean, how do you even evaluate a system like this?
You can't just check the loss function, right?
No, because with the standard neural network, yeah, you just look at the loss function. If the loss is going down, your model is getting better. But in a Jan at equilibrium, the loss functions for both networks converge to these totally uninformative, oscillating values.
That's the ultimate paradox here. You are trying to write a reliable test suite, for a system that is literally designed to lie to you.
Exactly.
And visual inspection obviously doesn't scale. You can't have humans sit there and look at millions of generated thumbnails to see if they're getting better.
You'd need an army of interns. So the industry had to invent entirely new statistical metrics just to measure progress.
And the most prominent one became what? The friction inception distance?
Yes, FID. Because instead of doing a naive pixel-by-pixel comparison...
Which is useless, by the way.
Right, because a generated face shifted 1 pixel to the left is mathematically 100% different in RGB values, but visually it's identical.
So how does FID fix that?
FID runs the generated images and the real images through a separate pre-trained image classification network called Inception.
Okay, so it's extracting deep features. It's looking at the mathematical representation of, like, fur texture or eyeball shape, rather than raw pixel values.
Exactly. It extracts those deep feature distributions and then compares the statistical distance between the fake data set and the real data set.
So a lower FID score means your fake images closely overlap the statistical reality of your training data.
Right. But even FID was just a proxy metric, and clever architectures could still game it.
It became pretty obvious that researchers couldn't just tweak learning rates to fix these pathologies. They had to rip out the foundation.
They needed a totally new architecture.
Right. And in 2016, a major breakthrough happens with deep convolutional GANs, or DCGAN, developed by Alec Radford and his team.
This was huge.
Because up to this point, GANs were using fully connected layers.
And fully connected layers are a complete dead end for image generation.
Why is that?
Well, in a fully connected network, every neuron is connected to every pixel. So if you want to generate even a tiny, like 100 by 100 pixel image, you are dealing with tens of millions of parameters in a single layer.
The memory requirements just explode.
They do. That's why early GANs could only output those blurry, postage stamp-sized images. So Radford's team stripped those out entirely and replaced them with convolutions.
Now, I know standard convolutions are used in image recognition, right? They act like a filter sweeping across an image, compressing it down to find features like edges or corners.
Yep, pooling the data.
But DCGAN used transposed convolutions in the generator. What is transposed convolution actually doing? Is it just running the compression in reverse?
That is actually a great way to visualize it. It's sometimes called unpooling or fractional striding.
Untooling, okay.
Instead of taking a 4x4 grid of pixels and summarizing it into 1 pixel, a transposed convolution takes a single value from the noise vector and projects it outward.
Like expanding it.
Expanding it into a 4x4 grid of pixels, it sweeps across the latent space, progressively upsampling the mathematical noise into a full-resolution spatial image.
Okay, that makes sense. The DCGAN recipe also heavily relied on leaky rail U activations, right, to prevent dead neurons in the discriminator.
Yes. Crucial detail.
Let's unpack that for a second, because dead neuron is a term thrown around a lot. What actually kills a neuron in this context?
So a standard ReLU activation function is basically a mathematical gate. If a value is positive, let it pass. If a value is negative, turn it into exactly 0.
Right.
The problem is, once a neuron's output hits 0, the gradient, that feedback signal passing through it, also becomes 0.
So the neuron just stops updating its weights entirely.
It dies, and in a GAN, a dead neuron in the discriminator creates a permanent, unfixable blind spot.
Which the generator will immediately exploit.
Immediately.
So leaky rail U fixes this by adding a tiny slope.
Right.
Instead of turning negative numbers to 0, it turns them into a very small negative fraction, ensuring the mathematical signal keeps flowing.
Exactly. It keeps the game moving.
But DCGAN didn't just solve stability. It proved something mind-blowing about how the AI was organizing information.
So, the latent space arithmetic.
Yes. It proved you could do math with concepts.
This is where we realize the network isn't just memorizing pixels, you know.
Okay.
It's mapping concepts to actual spatial geometry. Every generated image corresponds to a specific coordinate, a vector, in this high-dimensional latent space.
And they discovered that if you take the vector coordinate that generates an image of a man with glasses, right?
Yeah.
And you mathematically subtract the vector for a man without glasses, and then add the vector for a woman without glasses.
You don't get a corrupted image.
No. The generator spits out a perfectly coherent image of a woman with glasses.
It had isolated the mathematical essence of glasses and gender.
When I look at that, my software engineer brain instantly maps it to object-oriented programming.
How so?
Well, the AI naturally learned to treat incredibly complex organic visual concepts as highly modular, injectable variables.
It's like it built its own internal API for reality.
Exactly. So with that geometric foundation solid, the industry raced to scale. But DCGN was only generating 64 by 64 pixel images.
Impressive for 2016, but scaling to 1024 by 1024 photorealism is a massive hurdle.
Because the pixel count doesn't just double.
No, it jumps by a factor of 256. And the discriminator's job gets 256 times easier because there are millions more pixels to spot a fake in.
Which instantly causes that vanishing gradient problem we talked about earlier.
Instantly.
So how do you solve that? Enter Progressive Jan in 2018 by Tero Karras at NVIDIA.
A brilliant approach.
And their solution wasn't a new mathematical formula. It was essentially an elegant curriculum design.
Right. They stopped trying to force the network to learn high resolution instantly. Instead, they started training both networks at a microscopic resolution. Just 4 by 4 pixels.
16 pixels total.
Just 16 pixels.
At 4 by 4, the network can't even render an eye. It's only learning massive, coarse structures, like where is the center of mass? What is the general skin tone?
Exactly. And once the networks reach a stable equilibrium at 4 by 4, Karras dynamically faded in a new layer of neurons to double the resolution to 8 by 8.
And then 16 by 16.
All the way up to 224. The coarse layers act as an unbreakable, stable foundation.
So by the time the network is generating megapixels, the heavy lifting of composition is already solved.
The highest resolution layers only have to focus on micro details, like hair strands and skin pores.
That curriculum is what gave us the first AI faces that truly stunned the public.
It really was a turning point.
Which sets the stage perfectly.
Yeah.
Because once you achieve high-resolution photorealism, the next logical requirement for any tool is control.
Right. An artist doesn't want a random face. They want a specific face.
They want to tweak the lighting or change the hair without altering the bone structure. That brings us to StyleGAN.
StyleGAN arrived in 2019, and it fundamentally altered the generator's architecture. Instead of feeding the random noise vector directly into the bottom of the image generator like before, they ran the noise through an entirely separate neural network first.
This is the 8-layer mapping network.
Yes.
And the purpose of that mapping network is to warp the raw, unstructured noise into a highly organized style vector.
Then they inject that organized style vector into the image generation process at every single resolution level.
Using an operation called adaptive instance normalization, ADAIN.
ADAIN, yeah. Without getting bogged down in the calculus of it, ADAIN essentially overrides the statistical mean and variance of the image features at a specific layer, forcing those features to conform to the injected style.
The result is disentanglement.
Complete disentanglement.
Because they were injecting styles at different resolution layers, the network learned to separate human features. The coarse styles injected at the 4 by 4 level exclusively controlled big picture geometry, right? Like face shape, head pose.
While the mid-level injections controlled hairstyle.
And the fine-level injections controlled skin texture. You could literally take the bone structure of person A and seamlessly inject the freckles and lighting of person B.
This is the exact architecture that powered that viral website, "This person does not exist."
Right, but generation is only half the story. While Karras was scaling up resolution, other researchers in 2017 hit a completely different wall, which was image translation.
Turning a sketch into a photo or a daytime scene into a nighttime scene.
Early models like Pix2Pix could do this, but they required paired data.
Right. If you want to teach an AI to turn a satellite map into a street map, you need thousands of exact one-to-one pairs.
But in the real world, paired data is a massive luxury. I mean, if you want an AI to translate photos of horses into zebras,
you don't have a data set of a horse standing in a field, and then a photo of that exact same horse in the exact same pose painted with zebra stripes.
Exactly. So StyleGAN solved this unpaired translation problem using something called cycle consistency loss.
They trained two generators simultaneously. Generator A translates horses into zebras. Generator B translates zebras back into horses.
The mathematical constraint they introduced is just beautiful. If you pass an image of a horse through generator A and then pass that output through generator B, the final image must mathematically equal the original horse.
It's a classic round-trip API test.
Yes. Or think of it like bidirectional data serialization.
Oh, good analogy.
If I take a complex object in memory, serialize it to a JSON payload, and then parse that JSON back into a new object, it better perfectly match the original. If I lose data, the serialization logic is completely broken.
And that cycle consistency forces the network to preserve the core payload of the image, the background, the lighting, the exact posture of the animal.
Because without that round-trip constraint, the generator might turn a horse in a grassy field into a zebra standing in a zoo.
Just because it's easier to generate zoo backgrounds.
Right. The cycle loss prevents hallucination. So this era produced an explosion of specialty GANs. You had conditional GANs you could prompt with text labels.
SRGN, which acts like the enhance button from a crime show, just hallucinating hyper-realistic details into pixelated security footage.
And Gauguin, where you draw MS Paint-style color blocks labeled mountain or water, and it generates a photorealistic landscape.
It was a wild time.
Listening to this timeline, GANs sound utterly invincible. They're doing math with concepts, they're achieving photorealism, they're manipulating reality, and yet, if you look at the generative AI landscape today, GANs have largely been abandoned as the foundational model.
It really is one of the most dramatic architectural shifts in recent tech history. The industry moved to diffusion models. DALL-E, Midjourney, Stable Diffusion.
And why do they abandon GANs?
Because GANs never fully escape their foundational flaws. All those engineering tricks we talked about, the transposed convolutions, injecting style vectors, applying spectral normalization, and gradient penalties.
They were ultimately just incredibly sophisticated duct tape.
Exactly. They never cured the inherent fragility of the Minimax game.
You could be training a GAN for 3 weeks. It looks amazing at epoch 100, and then completely collapses into visual garbage at epoch 150 for literally no discernible reason.
Furthermore, GANs lack an explicit likelihood measurement. You cannot ask again, what is the mathematical probability of this specific image occurring in the real world?
And because of mode collapse, their statistical coverage was always flawed.
Always. A GAN might generate a million gorgeous, convincing faces, but a deep statistical analysis would reveal it was subtly ignoring rare ethnic features or unusual lighting conditions that were present in the training data.
It only generated what was easiest to fool the discriminator.
Right. And diffusion models solved this by replacing that adversarial street fight with simple, stable regression.
Let's clarify that shift real quick. A diffusion model takes an image, slowly adds static noise to it step by step until it's pure static, and then trains a neural network to simply reverse that denoising process.
It is incredibly stable to train. It maps the entire distribution of the data set without dropping modes, and it provides explicit mathematical likelihoods.
But I want to push back on this just a bit.
Okay, go for it.
If a gene generates an image in a single forward pass, literally one matrix multiplication, and a diffusion model has to run its denoising loop dozens or even hundreds of times to generate a single image, why on earth would the industry accept a system that is exponentially slower and more computationally expensive?
Because in enterprise software, stability and reliability almost always beat raw speed. A slow model that reliably produces a diverse, high-quality output every single time is vastly more valuable than a blazing fast model that occasionally collapses or ignores edge cases.
That makes sense.
However, GANs are far from dead.
Where are they surviving?
They still dominate domains where real-time speed is the absolute bottleneck.
Oh, like rendering.
Exactly. If you are dynamically generating textures in a video game running at 60 frames per second or applying a live photorealistic filter to a video stream, you cannot wait for a diffusion model to denoise.
You need the single pass speed of a gene.
You have to have it.
It is the ultimate architectural trade-off for a developer.
Truly.
So what do we take away from this deep dive? To me, GANs prove something profound about the nature of computation. They took this deeply human intuition that meaningful creation and continuous improvement can emerge entirely from competition, and they formalized it in code.
Ian Goodfellow basically wrote a while loop for the creative process.
An artist gets better by studying the masters, facing relentless critique, and refining their technique.
GANs proved that you don't need a mathematical formula for good, you just need an adversarial environment that punishes bad.
I challenge you to look at the system architectures you are working on right now. Is there a stubborn bottleneck in your project? A heuristic that is nearly impossible to optimize programmatically?
It happens all the time.
Ask yourself, could introducing a little adversarial pressure, setting up a dual system competition, solve that problem organically?
It is a phenomenal lens for problem solving.
And I'll leave you with one final thought to ponder while your code compiles. What if we took the exact Minimax game, the core DNA of a GAN, and applied it directly to software engineering itself? Imagine an AI generator whose sole, singular purpose is to write application code. And it is locked in an internal automated arms race with an AI discriminator whose sole purpose is to write edge case unit tests designed specifically to break that code.
Just testing it to death.
How quickly could a system like that evolve entirely on its own without a human ever touching the keyboard?
A fascinating and a slightly terrifying possibility.
Something to think about.
A lot.
Thanks for taking this deep dive with us.